Hello everyone. I thought one of the best things that we could do before we get into the complex stuff in the motion unit, in the kinematics unit, is to make sure we all have a really good understanding of the big principles that you would have learned from the graphing unit that you did in kinematics in grade 11. So I've created this works for me really nicely in my head, so I thought I would share it with you. I've created this kind of graphing summary. We're going to look at uniform motion graphs first and look at how we move from one graph to the next. And then we'll do the same thing for non-uniform motion in the context of uniform acceleration. So we're going to start off here first and look at 4 possible different dt graphs. So what I'm doing here is just kind of making a sketch of what's happening with the motion. You can see we've got a straight line on the dt graph. So if we've got a straight line, I should be more specific, a straight diagonal line, then that means that the object is moving with uniform motion. It is not changing its speed. It's covering the same amount of difference in each time interval. And usually we like to make that time interval second by second, it's covering the same amount of difference in each of those seconds. So let's take a look at the first one that I've got here. That's our first one. And what I like to do when I'm looking at the dt graphs, because they give us a little bit more information, especially since I've drawn these ones out of the 0 spot, the origin spot. So they give us some information. They tell us which direction the object is moving, and the direction is determined by a positive or a negative slope. That might be something that you want to write down. I'm probably not going to write down too much on mine, but write down what you need as we go through it. So the direction, this is something very unique about the dt graph. The direction is determined by positive and negative slope. That's not the case for the vt graph and the at graph. They both determine their own directions differently than the dt graph. So if I look at the first one here, I can say this one's moving away from an origin, and maybe we don't want to even call it an origin. Maybe we want to call it like a starting point or a home location. Like say it's your home. You left your home and you walked a certain amount of distance in, let's say, 10 minutes, and you did that uniformly, and you went, that distance that you went, that position that you went, was all in the same direction, because it's all in that kind of positive direction along that d-axis there, right? And so it went positively along the d-axis. So we've got moving away from home or positively away from home. And we know that we're moving in the positive direction here because we've got a positive slope. And then we also know that the slope of the line tells us something. The slope of the line tells us the velocity. So we take the slope of the line here, we can actually take that slope and we can plot it on the neighboring VT graph. So our first one will look straight line on the VT graph. And I knew to put it above the t-axis. This is really important. On the VT graph, I knew to put it above the t-axis because that is positive velocity, and it's doing the same velocity the entire time of the time interval given there. Okay, so those match really nicely. The VT graphs, though, they don't care about the starting point. They don't care about the starting point at all. They don't care about the origin. They are more concerned with what direction is the object going and is the object changing its velocity. And then the cool thing is to go from the dt graph to the vt graph, and then to take the vt graph and go to the at graph. We are always using the same concept. We are taking the slope of the line. This is really cool because there's going to be an application for you later on when you do calculus that this is actually called the derivative. You're taking the slope of the line and you're plotting that one graph over, because we're looking at how these are related. Okay, so to go from the dt graph to the vt graph to the at graph, it's always slope of the line. I'm going to write that down. That feels kind of important. I'm going to say to go, let's make a different color. To go this way, we use slope of the line. That's your technique that you want to use. Okay? Make that blue again. And then, of course, if I'm looking at this VT graph, it has a slope of 0. Perfect. That means no acceleration. So it's going to go right on that 0 spot on the AT graph. And that makes sense. Even if you go back to your original DT graph, you expected no acceleration. You probably don't even need to go from one to the next in order to get there. You knew there was no acceleration happening as soon as you had a straight diagonal line on the DT. All right, let's try the next DT. This DT right here, it's got a negative slope. So that tells me it's moving in the negative direction. And it looks like it started away from our home or our starting point. And as it got closer to the end of the time interval, let's see where it is there, it's actually back at home. So it's moving in the negative direction back towards home. The VT graph, of course, doesn't care about the starting point. All it cares about is what direction is this and is it changing velocity. This is a negative slope. To show negative velocity, so we calculate, if you actually calculate this out with numbers, sorry, my brain's jumping around. If you calculate this out with numbers, you're going to get a negative number, right? So if you take that negative number, it actually should get plotted below the t-axis, so below where the V is 0 spot is, it should get plotted right there. And it should be a nice straight line as well. Okay? So they correspond beautifully together. And then of course, nice and easy from the VT graph to the AT graph. There you go. No acceleration there. Why not? The slope of this line is 0. Cool. Let's try the next one. This DT graph over here. Oh, it looks like we're moving away from home, but we're going in the other direction away from home than we did before. So say that this one was like we moved north. Pick north because it was up. Totally random. Could be positive. Could be west. Could be east. Doesn't matter. It's whatever you assign it at the beginning or whatever is assigned in the question that's given to you. So if we said that this was north, this kind of means we're moving south. We're moving away from home, south, in the negative direction. That velocity is going to be a negative velocity. All right, so that means we take the slope of this line here, slope of that line, and plot it over on our VT graph. Okay, we can easily do that. Whoa, we've got two VT graphs that look the same here. But what we want to notice is that VT graph does not care about where the object started from. So you can tell by looking at the DTs. These two DTs give us different information in the context of the displacement time graph or the position time graph. In the context of the velocity time graph, all we care about is that it's negative velocity. This velocity is negative, and so that means the velocity is moving. Like if we assigned positive to be north, then south would be negative. So it's moving in the south direction. That's what that means. And it's moving at a uniform velocity. That's uniform motion, where our acceleration, once again, booyah, 0. Nice straight line, right? Nice straight line. Looks beautiful. Okay, the last DT graph right here. It is a positive slope. You can see that's a positive slope, so that tells me something. When I calculate this out, if you actually did rise over run or took 2 points and did the delta y over delta x, or in this case it would be delta d over delta t, you would get a positive value. If you're getting a positive value, that automatically means you've got to plot it there. But the information that we're getting out of this DT graph is that this thing is moving back towards home, like it's coming from the south, back towards home, moving in the north direction. Makes sense, right? It totally makes sense. And it's doing that at a uniform speed or uniform velocity. So once again, you can see these two middle DT graphs have the exact same VT graph. The two outermost DT graphs, these ones right here, look at that, they have the exact same VT graph because the VT graph does not care about your starting point. And then we'll just get that AT graph in there. Okay. The other key thing that you learned in grade 11 is that moving from the DT to the VT to the AT, we use the slope of the line. But if we wanted to go the other direction, if I gave you the VT graph, for example, and you had to go from the VT graph to the DT graph, you would use a different technique. And that technique, see if I can bump this up a little bit, is area under the line. So to go from this way, you would use area. And it's always the area that we're talking about is always the area between the line or the curve. It could be a curve. Hopefully it's not, but it could be the curve. Always the area between the line and then the axis. So you'd like see in this spot right here, you would actually make yourself a nice little rectangle, take the area, and that area would give you the position, how far the object has gone in that time interval. And that's what you would graph over on your DT graph. You're going to get a little bit of practice of this if this seems a bit rusty, because for some of us, this has been a while. The thing is that we noticed that this would be a negative area. So that means that we would have to have a negative movement on the DT graph. So that's how I would know to do this kind of spot. I would pick a starting point. Would it matter? If I was given this VT graph and that's what I started with, it wouldn't matter. I would actually even probably start out of the origin, right? Because it just makes a little bit more sense. Nobody told me this graph, which is also the same as this, but nobody said anything about, oh, it starts from a certain location and goes back towards a starting point. There's no information built into that VT graph. That would actually have to come through text or through a conversation. You'd have to get that information somewhere else. If I don't get that information, I'm going to take the area of that line and I bet you I'm going to draw that one because it's easier. Out of the starting point, it still shows the same. Traveled this far in that given time, and that gives us a constant velocity that's negative so that those two correspond as well. Okay? So that's a little bit of a quick little overview of the uniform motion. Let's take a look at the next one. So now we're going to do a non-uniform motion, which is in the context of uniform acceleration. Just like in grade 11, we don't expect you to deal with the step above that, which is like looking at what the slope of a diagonal line would be on an AT graph. Okay, so I paused you there and you didn't notice, ha ha ha. And now there's all this stuff written on your screen. So take a moment to maybe get yourself caught up on the non-uniform motion. This is uniform acceleration. And I have drawn, look at, yeah, maybe we do need the lightsaber for this one. What do you think? Yeah, we do. Oh yeah, you like that, right? I have drawn some really very good sketches, if I do say so myself, on the iPad Surface. But you'll notice that I've kept them all in the positive area on that DT graph. And it's really important for you to note that we could shift these up and down. Oh, maybe you did those in grade 11 math where you shifted the graphing stuff, the functions up and down the y-axis. It's the same kind of thing that's happening here, because once again, that VT graph doesn't really care where the object started. So I've started at the origin or I've ended at the origin just for simplicity's sake, but that doesn't mean that if you didn't know, if you knew the information that it wasn't starting at the origin, you could totally do that. But my point is that we can shift these. You could take this exact same shape and do it down here, or you can do it up here. It doesn't matter. It's going to give you the exact same VT graph. Okay? All right. So for our VT graphs, for these ones are a little bit tricky. And the concept that you're supposed to use is the slope of the tangent, right? And the slope of the tangent, that's just because we know that when we're going this way, let's write this back up, same exact situation, slope when we're going from the DT, VT to the AT, and then bump it up. Let's do this while we're here. If we go this way, we're using area. That's the same as before. It's so great. Doesn't matter if it's uniform or not. We're using the same exact context there. Hope that's straight for you. You know what? Maybe it's my iPad case. It might be. You can probably hear me clunking around there. Sorry. There. I kind of like that. Okay. So, all right. So what we want to do is imagine that we've got to use the little mini slope technique, and that we call the tangent. Remember learning the tangent? You actually had to like pick a point. Oh, I totally didn't want to do that with the red. There we go. pick a point on the graph and then draw a little tangent, like a straight little line at that point. And then you pick another point and draw a straight little tangent at that point. And then you pick another one and you draw a straight little tangent at that point. They're kind of like little mini slopes. So what you can tell is happening here, that you started off really slow and ended up fast. And that's what I'm kind of, anytime I'm analyzing a graph, I actually have to still do that. It's just something that's really hard for my brain to accept. So I start off slow, pretty much stopped, right? Like that's the slope of a horizontal line is 0. So we start off stopped and we end up fast, and that's all happening in the positive direction. So you can see the overall slopes of the tangents that you would draw would end up being positive. So that means we've got a positive velocity, but we've got to show that we originally started off stopped and ended up with a fast speed at the end. And in order to do that, we've got to do straight diagonal line on the VT graph. Sorry, I probably drew that a little bit too far. Let's see if we can. There. Oh yeah, that looks good. I was just so excited. Straight diagonal line on the VT graph. And the key thing to note is that they correspond beautifully together, but you actually have to think about it. Ask yourself, what direction is the motion? It's clearly non-uniform, so it's uniform acceleration. What direction is the motion? And is it moving from slow to fast or fast to slow? And sometimes we can replace the word slow with stopped if you've got a perfectly horizontal line. Okay? So just take note of that. That's one thing that I'm always looking at. What's the direction? You might want to write that down. What's the direction? And then what's the motion doing? Is it fast to slow or slow to fast? Okay, then the exact same concept happens when we move from the VT to the AT. Let's take a look at this graph, this VT graph right here in the center. Slope of that line, hey, it kind of looks like your DT graph in uniform motion, eh? Take the slope of that line, and what would you do? If it were a DT graph, you would plot it like that, right? Just back it off on the end there. There you go. You would plot it like that. So it's so interesting because in the uniform acceleration or the non-uniform motion context, these two look like they were the old DT and the VT from before. Interesting. Interesting thing that we've got here, we can see this is where we're stopped. This is where velocity is 0. Velocity is bigger over here. This is the positive end of the velocity scale. And then you've got an increasing speed you're showing from stop to fast in the positive direction. And then if you take the slope of that line, that gives us the direction of the acceleration. And remember, the acceleration, this doesn't mean necessarily that we've got that positive acceleration actually means speeding up and negative acceleration means slowing down. You remember from grade 11 that there are two things that you need to have in order to understand if something's speeding up and slowing down. The positive or negative sign on the acceleration is always just representing the direction, like north or south. It's not telling you if it's speeding up or slowing down. The two things you need are the sign of the velocity and the sign of the acceleration. So these two together, I've got positive velocity here, positive acceleration here. Guess what that is? That is speeding up. Oh yeah. Let's try the next one. The next one also overall would have a positive slope. Let's take a look here. Let's take a look at some mini tangents that we would draw. Steep mini tangent here, flatter mini tangent, flatter still. Ooh, maybe we can almost get completely to a stop there. So we're going fast to slow in the positive direction. Think about that. Give yourself a moment. See if you can draw that on the corresponding VT graph. Fast to slow in the positive direction. So it should look like that. And that has to be the exact placement of it because it has to be moving in the positive direction. This is always the tricky one for students because you see that negative looking velocity slope and you're like, yo, that means it's negative. But that's not where direction is told on the VT graph. The direction is told by placement above or below the t-axis. So make sure you're taking a look here. This is positive velocity, but it is slowing down. Take the slope of that line. What's it going to be? It's going to be negative on the AT graph. Let's tie all these things together. It's so exciting. Look at fast to slow in the positive direction on that DT graph. Overall, this thing's moving positive, which means we have to be above the t-axis on the VT graph. But we've got to show fast originally means we're starting up high, and then we're approaching that 0 spot. We take the slope of this line, and it's negative. So I've got positive velocity, negative acceleration. What do we call that? Slowing down. Yes. Feeling good. Okay, do you think you can do 2 more here? Let's take a look. Let's describe this one first. This one I'm feeling overall negative slope. If I were drawing mini tangents, they would all be tilted to the left. They start off fast and end up stopped. So to me, that means start off fast, end up stopped in the negative direction. If it's in the negative direction, that means I'm below the t-axis on the VT graph. Like that. What do we say about that acceleration? If we're going to use the acceleration, we're going to take the slope of the VT graph, and we're going to say that, hey, that is a positive slope, right? That is a positive slope. So when if I calculated that out, that would actually end up like so. What have we got here? We have got negative velocity because it's below the t-axis. Don't get tripped up on that positive slope there. That positive slope, think about what the slope of the line really means. It means acceleration. It's meters per second divided by a second. So when you do the slope of the line, so that is the acceleration, and that acceleration gets plotted over here. So we've got negative velocity, positive acceleration. That means slowing down as well, and that's a good thing because over here on the DT graph we said fast to slow, slowing down. Wicked awesome. Who is having fun? I don't know about you, but I'm having a good time. Okay, so this DT graph here, it is also got an overall negative slope, starting stopped, and then you can see how the graph is kind of tilted to the negative direction. If I were to draw mini tangents, you would notice they're all tilted to the left, and they start off stopped and then get faster. Do you think you can plot that VT graph on your own? Give it a try. Starts off stopped, gets bigger, but is in the negative direction. So if it's in the negative direction, it must be below the t-axis and look something like that. Nice straight line, diagonal line coming out of the where velocity is 0 and getting bigger in that negative direction. So that's a perfect representation of what's happening here. These two are beautifully connected. And what we want to show is that we know what's going to happen here when we go to the AT. We take the slope of this line, and it is a negative slope. So that means on the AT graph, it's below the t-axis. And we can compare our, gotta switch over to the pointer. We can compare our velocity direction and our acceleration direction. Velocity is negative, acceleration is negative. That means, friends, speeding up. No surprise, because we went from stopped to fast, but we did it in the negative direction. And just like with the uniform motion graphs that we just did on the previous page, you will notice that there is a link between the graphs, but in the opposite direction. So that means if you're given the AT graph, you can technically work your way backwards by taking the area of the line, the area between the line and the t-axis, getting that area from an AT graph will actually give you the velocity that that object ends up at after a certain amount of time. Okay, so whatever the time interval is that it ends at here, that will give you the final velocity. You're going to assume the beginning velocity was whatever, make it easy on yourself. It doesn't really matter because you don't know if its initial velocity is 0 or not. You don't know that. But you can take the area of this graph will give you a change of velocity essentially, right? And as long as you're showing that change on a VT graph, it doesn't have to come right out of the origin there. It can do that too. And then once you know this graph, then you can take the area of it as well. And once you have its area, that means you know how far the object moved in that time interval. And then you can graph that too, which is really tricky to do. Really, really tricky to do. But possible with a little bit of practice. Okay, I hope this is a really good summary for you and you feel comfortable using this as a resource anytime you need to. I love this summary. For me, when I was learning the graphs, this really kind of summarized everything nicely for me, and I felt confident that I could take this out anytime I was doing any questions and make sure I understood that stuff well. So I hope it's helpful for you, because we're going to spend 2 days going through all of the graphing that you did in grade 11. Awesome. Looking forward to it. Have a good one, everybody.